Every second, Facebook answers 1 billion questions about who's friends with whom. Not a typo. 1 billion, every single second, forever. If this were a real postal system, every person on Earth would need 130 letters answered per second, non-stop. Here's how Meta built a machine fast enough to make that boring. In 2013, Facebook's social graph held hundreds of billions of friendships, likes, and comments. For every single write, 500 reads followed it. Every read needed sub-10 millisecond latency, always, and 500 million new connections got added daily. No normal database was ever built to survive math like that. Picture a user with 5,000 friends. Get all friends means joining across multiple tables, scanning millions of rows. Now multiply that by a billion requests per second. A single MySQL instance chokes instantly. This is where naive relational design collapses. Facebook needed something built for graphs, not spreadsheets. Think of TAO like a global postal system. Local post offices answer most requests instantly. Regional sorting hubs coordinate, one per neighborhood. A central records office keeps the permanent archive, and every person's ID already contains their home post office's zip code. Let's build this piece by piece. TAO doesn't store rows and tables. It stores objects, users, posts, photos, and associations. Directed edges like liked or friend. A like is just user123 liked post 789 at time X. Every Facebook feature, feeds, friend lists, like counts builds from 4 simple graph queries. Here's what nobody tells you. Facebook intentionally shows you stale data every single day. A like count that's a second old? Totally fine. TAO trades perfect accuracy for raw speed, because for social media, fast and 99% right beats slow and 100% right every time. TAO's defining trick, 2 cache layers between clients and the database. Follower caches, hundreds per data center, answer reads directly like local post office windows. Leader caches, 1 per shard, coordinate writes like a sorting hub. MySQL sits behind everything as the permanent records office. Here's a read in action. Your app asks the nearest follower cache for user X's friends. Cache hit, answer returns in microseconds, mail delivered instantly. Cache miss, the follower asks upstream, MySQL gets queried, and the cache fills for next time. Only misses ever touch the database. The math is brutal in Facebook's favor. A cache hit, under 1 millisecond. A cache miss, 10 to 20 milliseconds hitting MySQL. With a 96% hit rate, almost every one of those 1 billion reads per second never touches a database at all. That's the entire trick. Writes work differently. A like goes straight to the shard's leader cache. The leader updates its own cache, writes through to MySQL, then confirms success. This is write-through caching. The leader guarantees its own data center never serves outdated answers after a write completes. But writing to one leader doesn't fix stale copies elsewhere. So the leader mass mails change of address notices, invalidation messages, to every follower cache holding that data. It's exactly like a post office sending this address moved cards. The next read on those followers forces a fresh fetch. What about other continents? MySQL replication ships the write to secondary data centers. A daemon reads MySQL's bin log, its change log, and sends invalidations overseas. This takes 100 to 500 milliseconds. For that window, Tokyo might see an old like count while California sees the new one. This eventual consistency is a deliberate trade. A like count that's briefly stale? Fine, nobody notices. But privacy, can user Y see user X's private photo, cannot be wrong even for 100 milliseconds. Different data, different rules. That's the postal system choosing which mail gets priority delivery. Here's the clever part. Every 64-bit object ID secretly contains its shard number, baked in at creation, like a zip code stamped on your ID at birth. 41 bits timestamp, 13 bits shard, 10 bits type. That ID never changes, so TAO always knows exactly which shard owns it. Why bother? Because associations live on the shard of the first object. Query get user X's friends always resolves to exactly one shard, no cross-shard scattergather. It's like knowing a letter's destination post office just from its zip code, before you even open the envelope. Friendship is bidirectional, but sharding is one-directional. So TAO stores it twice. X friend Y on X's shard, Y friend X on Y's shard. Reading either person's friend list still hits just one shard. 2 mailings, one consistent relationship, written together so they never disagree. Zoom out to global scale. Every shard has exactly one primary data center. All writes for that shard go there. Other data centers hold read-only followers, kept in sync by async replication. Every person has one home post office worldwide. even while local branches everywhere hand you your mail. Here's the catch. If you're in Europe but your shard's primary lives in the US, your write can't stay local. The EU cache uses a forward pointer to route your friend request across the ocean. That round trip costs roughly 100 extra milliseconds, the price of global consistency. One more trick. After you write something, TAO makes sure you never see your own stale data. Your web server remembers what you just changed and forces a fresh read, bypassing the cache for a short window. You always see your own like. Everyone else might wait. The most common query isn't get one thing, it's get the last 20 likers of this post. TAO caches these sorted lists as one unit. A new like just prepends to the cached list. No requery, no resort, just insert at the front and move on. This is literally how your newsfeed gets built. Get your friends list, one TAO call. For each friend, get their last 5 posts, more TAO calls. For each post, get like and comment counts. A single feed load can trigger hundreds of TAO reads, all in single-digit milliseconds. Privacy checks break every rule above. Can user Y see this photo? Can't tolerate 300 milliseconds of staleness. That's a security hole. So TAO forces these reads straight to the primary MySQL in the US, skipping the cache entirely. Slower? Yes. But correct beats fast when privacy is on the line. The 2013 TAO paper published the receipts. Over 99% of reads served entirely from cache. Billions of objects, hundreds of billions of associations, sub-millisecond hits. This wasn't a thought experiment. It was already running Facebook's newsfeed, notifications, and ad targeting for over 1 billion users. How did we get here? 2005. Facebook ran on plain MySQL. 2009. Memcached patched over the cracks, but invalidation was chaos. 2013. TAO launched, purpose-built for the social graph. Today, that same architecture handles over 1 billion graph reads every second for 3 billion users. Zoom out and compare. A naive relational database, cross-table joins, manual caching, invalidation nightmares, breaks past millions of users. TAO, graph-native queries, automatic write-through caching, 1 shard per query, proven to serve billions. Same problem, completely different architecture, completely different outcome. In your next system design interview, say exactly this. For read-heavy graph data, I'd use a 2-tier cache, followers for reads, 1 liter per shard for writes, with write-through invalidation, routing only consistency-critical reads to the primary. That sentence alone signals real production experience. TAO isn't unique to Facebook. Twitter's FlockDB solved the same graph problem. LinkedIn's economic graph faces identical read-heavy patterns. Anywhere you have a social graph, friends, follows, likes, you'll hit the same fork. Relational databases don't scale, so someone builds a cache-through graph store. Remember the Postal System? Follower caches are your local post office windows. The leader cache is the regional sorting hub, 1 per shard. MySQL is the permanent records office. And your object ID is the zip code stamped on your identity the moment you're created. Zoom out one last time. 3 billion users, hundreds of billions of connections, 1 billion reads every second. A 96% cache hit rate keeps almost all of that traffic away from any database at all. That's not luck. That's architecture, deliberately built for this exact problem. That's TAO, a global postal system for the social graph, where local post offices handle the flood, 1 sorting hub per shard prevents chaos, and every ID carries its own zip code. Next time caching at scale comes up, you'll have the answer. Subscribe for the next deep dive.